continuity is required for a lot of the calculus stuff that we do. So the non-mathematical idea, I like these pictures. The non-mathematical idea, this is just continuous everywhere. Okay, there's no interruption or break, and obviously there's an interruption here. We had a little bit of an issue. So this is non-mathematical. I think that you could grasp this idea of what is continuous and what is not. But mathematically, we need a definition, and we definitely need a definition at a point. What is continuity at a point? So this idea of continuity of a function at x equals c, or to be continuous at x equals c, or continuous for all x's in a specific interval from 3 to 5, or that kind of a thing. So we are very careful about how we ask about continuity in calculus. So it has a mathematical definition, and we need to make sure that we understand these conditions. So these, like I would put a huge star by these. We're going to make sure that we write out these conditions because they're very important. So continuity occurs at a point. Continuity at a point occurs. I should probably say that actually. Continuity at x equals c. All right, that should go right there. At a very specific point. Occurs if and only if these three conditions are met. Number one, f of c is defined. So I have to have a value, a y value, at x equals c. Okay, that must happen. So what that means is that the point exists. Okay, try to break this down for you. You will use this. Right? This is not something that you're just going to leave off. You're going to have to use these conditions quite a bit. So I want to make sure that you understand what they mean. The second condition is that the limit of the function as x approaches that value must exist. Okay? So I have to have a value. So this would mean that the limit exists. So now that we've evaluated limits, we know that the point has to exist, the limit has to exist, and then finally, and most importantly, the condition that has to be met is that the function value has to equal the limit. All right? Remember, the limit is, I'll rewrite that. Let me write that all the way out. Has to equal the limit as x approaches c of f of x. So the value and the limit have to be equal to one another. So this concept is that the y value at x equals c equals the limit value. So we will use these conditions over and over and over again. So a great graph to kind of analyze this would be this graph here. If I had c, let's do this. I'm going to make a function that just kind of curves. I'm going to have a hole there, like so. And then I'm going to have a point here. So keep in mind that this value, that is the function value. And this value right here, let's do that. This value right here, that is the limit value, okay, at x equals c. So if I were to go through these conditions, which you will be expected to do, looking at this graph, I would say, well, does f of c exist? Okay, f of c is defined. Absolutely. Okay, it has a value. That value is this y right here. Okay, so I do have a y value at x equals c. So that's one check. Okay, is the limit defined? So the limit exists. Okay, the limit exists. Yes, because the limit from the left is equal to the limit from the right. I can see this on this path. I'm approaching L. Okay, so that works. So the last one is, are they the same? Does f of c equal the limit? And in this case, it does not. Okay, I'm approaching two different y values here. So those are not equal. So this is not continuous based on these three conditions. Okay, we are not continuous at x equals c. So we would say not continuous. Now, I'm at a very specific point. I didn't say that the function wasn't continuous. I said that the function's not continuous at x equals c, and that matters. Okay, so be very, very careful with that. Let's actually make a couple of notes about that continuity at a point concept. So calculus deals with continuity at a point. All right, so let's make sure that we understand that. Calculus deals with continuity at a point. So the idea behind that is that the whole function can be continuous everywhere. You can have a completely continuous function. Whole function can be continuous everywhere. Continuous everywhere. So we can have that, but on the side of that, okay, at the secondary concept of that, a whole function can't be discontinuous everywhere. So we can't say that the whole function is not continuous. Can't be not continuous. That's a double negative. So let's kind of rewrite that in a way that might make a little bit more sense. All right. We cannot say f of x is not continuous. Okay, we can't say it like that. We would have to say f of x is not continuous at a point, because we would be referring to a very specific issue that it has. So it's kind of impossible for that to happen. Also, be very careful. Okay, be careful saying it. For the function that you're dealing with, or the value. Or the x value. Okay, make sure that you are saying that f of x is not continuous at a specific point. Don't say it's not continuous. Don't say it's not continuous at the value or at the x. Okay, make sure that you are being as specific as possible. So when we deal with continuity at a point, okay, just to kind of wrap this up, we can say that the whole function is continuous, but we can't say that f of x is discontinuous or not continuous. We would have to refer to the specific point. So it's important that we understand that, because a lot of times with calculus, to deal with continuity, we deal with the discontinuity. If there's an issue anywhere in the graph, we want to deal with the discontinuity piece. All right, so it's important for you to make that interpretation and understand that.